Hello, guys. My name is Desmond, and I welcome you to my lesson for today, where we will be looking at your physical sciences, as you can see, the introduction to electric circuits. So, ladies and gentlemen, as always, please do allow me to say it is very much important that I say it is very, very much important because, honorable members, what I'm about to say, it's massively important, ladies and gentlemen, that I say a day without learning something new, it's a day wasted. By so saying, please, bandla la kaNkulunkulu, please do make sure that by the end of each and every lesson that I conduct, you learn something new. Very, very much important, ladies and gentlemen, over there. So, obviously, I have indicated that introduction to electric circuits is what we are going to be discussing in today's lesson. So, very quickly, without any waste of our precious time, I'm just going to take you through the notes that you need to always remember before you go writing your test or exam. So, this is actually a summary of all that you need to always remember or know at all the times when dealing with electric circuits. So let's see. This is what I'm having. Two types of connections, namely series connection, and again, number two, we've got parallel connection. So these are the main two types of connections that we will be looking at. So obviously, under series connection, that's where more resistors are added in series. That's what you need to remember. And lastly, honorable members, let me do this and say total resistance. Total resistance increase and total current decrease. Good people, that happens provided the EMF remains constant. That's all under series connection. So let's see. Under parallel connection, obviously, that's when we are having more resistors connected or added in parallel. This is what I'm reading there. Again, under parallel, lastly, total resistance. In this case, can you see what happens? It decreases. And then total current increase. Good people, all of this is provided that the EMF remains constant. I'm telling you guys, it might not make sense at this point in time, but just always remember that under series connection and parallel connection, we've got common words which are being mentioned there. We spoke about the resistance. We spoke about the current. We spoke about the EMF. Under parallel, again, we spoke about the resistance. We spoke about the current. We spoke about the EMF. Massively important, ladies and gentlemen, that at all the times you pay full attention to all the details. Hence, I've done this so that you guys remember that it is important to notice that under series and parallel, we've got these words which are common. So I think let's try to discuss more regarding the current, the resistance, and the EMF. So just remember this information, ladies and gentlemen. When it gets to that time where we need to solve exam type of questions, we might need to remember this information, and I will from time to time refer to this information. For now, just be aware. Don't cram all of this. Just be aware that under series connection, we've got those 2 points. Under parallel connection, we've got those 2 points. And most importantly, under series and parallel, we've got those common words, which we are now going to have a look at each word. Let me slide to my next page. So, can you guys see important current, resistance, EMF? The underlined is what we will be discussing on this slide. So let's see. The current is what we are going to be discussing. So let's see. The current, honorable members, it simply refers to the rate of flow of charge. Remember, guys, at all the times, the word rate, it means over time. The rate means whatever over time. In this case, what is the whatever? Remember, the rate means over time. What is the whatever? The whatever in this case is the charge. Which means when we say the rate of flow of charge, we are simply saying that whatever being the charge over time. What exactly is that, honorable members? That is the current. So that means the formula for calculating the current is charge over time. Simple as that. Let's not complicate it and leave it at that stage. So let's see. Someone is seeing something very nice there, a very beautiful drawing there. So let's see what's happening there, honorable members. A Christmas tree. You might always need to remember that a Christmas tree can help you to understand a type of a connection. So let's see. Remember, we are still discussing the current. Maybe very quickly, let's try to have a look at how the current flows. Maybe let me use a red marker there. So let's see. The current, honorable members, flowing from the right towards, from the left towards the right. You might realize that the current passing through there, it is the same as the current passing through there, passing through there, passing through there. Meaning the total current passing through that type of a connection, which is a series connection. This is where now we might need to refer to that statement. More resistors connected in series. More resistors connected in series. That's when we talk about a series connection. So, now when we talk about the current flowing through a series connection, as I've indicated, the current passing through there is the same as there. That is why we simply say the total current through a series connection, it's actually the same as the total current flowing through each connection along a series connection. Remember, this is what we call an ammeter. It is used to measure the flow of current. So that means this ammeter is going to read the same current as there, meaning the current flowing through that resistor, it is actually the same as the current flowing through that resistor. So I have discussed current flowing through a series connection. Maybe let's try to have a look at the current flowing through the next type of a connection. So this is now the current again flowing from the left towards the right. Hey, can you see something happens there? It now splits. The other current will flow through this side, and then now the other current will flow through that side, and then when it gets to that point, it joins and then it continues. So now you might need to realize that in this case, where you are having another type of a connection, being parallel connection. Let's see. That's where more resistors are connected or added in parallel. It is that first line there. So let's go back to our slide and discuss further. So let's see. I hope you guys did notice that the current splits in that case. Maybe let me try to spice things up and see if that is going to help you understand better. Maybe let me remove all of that, because all of that has been explained. I will still remember to explain to you that Christmas tree there. So let's see. Maybe let me try this and see if it's going to work. Okay, there you are having your current flowing, and then when it gets to that point, it splits. And then now, as it splits, it means portion of that current will flow through that side, and again a portion of that current will flow through that side. It gets there, and then what happens? It now joins. So can you guys see something very much important, honorable members? In this case, the total current, no, I don't need that one. So the total current in this case, you will realize that here you've got the total flow of current which splits in two directions. The current passing through there, you will notice that it's actually a thin when you compare with the current passing through there, because it has splitted in two ways, meaning the current flowing through this side, when you add it with the current flowing through that side, which is the current passing through that ammeter 2, when you add them together, they are equivalent to the total current. So that is why we say it splits, and then it joins again. You can see after joining there, it's back to that thick shading there, which is the combined current. So that means if the current coming from this direction, let's say, is 4 amperes, it can split accordingly. Maybe if this side is 2 amperes, here it's going to be 2 amperes, and then here it's going to be back to 4 amperes. If it's 1 amperes this side, then it's going to be 3 amperes this side. as long as when you add them together, it takes you back to the total. So you can see in this case, we are saying the total current, it's actually equals to the current flowing through ammeter 1 plus the current flowing through ammeter 2. That's what I'm trying to explain there, honorable members. So now let's move on to the next type of a connection. You might notice something interesting there. Let me quickly remove all of these. So remember, guys, everything that I'm explaining now, it's what you always need to remember. Do not try to cram all of that. It won't, or it might not make perfect sense now. But I'm telling you, as we continue, especially when we deal with exam type of question papers, it is going to make sense. So now examiner tried to spice some things up there. And this is what they might do. That type of a connection, do not worry that much. You will realize that you still have the current flowing from the left, let's say towards the right. Let me now do that and show as it splits. Can you see? When it gets there, it splits, meaning the other current will flow through the other side, and then the other one will flow through that side. It gets there, and then it joins, and then now you are having that total current. Again, the same explanation regarding current in this case can be explained. So let's see. I actually want that one there. Okay, so let's see. In this case, honorable members, in this case, you might need to realize that we do have a parallel connection, and within the parallel connection, you still have a series connection, which means whatever that you learned regarding a series connection, it applies in this case. So it's like 2 in 1, if you can think of it that way. 2 types of connections within one. So it's more like this is a parallel connection, and within that parallel connection you still have a series connection. So remember, we are talking about the current, honorable members. So let's discuss the current. What happens to the current in this case? Obviously, it flows as total and then it splits. So that means the current passing through ammeter 1, when you plus it with the current passing through ammeter 2, honorable members, it has to take you back to that total current. So that's what I meant there to say the total current in this case, it's actually the current passing through ammeter 1 plus the current passing through ammeter 2. This is ammeter 1, this is ammeter 2. Again, honorable members, again, the current passing through ammeter 1, which is the current passing through there, on that side where we are having a series connection within that parallel connection, the current passing through resistor 1, it is the same as the current passing through resistor 2. It is as easy as that. Do not complicate it that much. Just always remember that. In this case, we are talking about the current which is measured in amperes. So now let's see. I think I might need to remove all of that and quickly tell you guys how I crammed these things. It was during my time when I was trying to actually make sense out of these things. It wasn't easy, but I finally found a way to easily remember these things. Maybe let me do this. Which color can I use? Maybe let me use yellow. Might not be clear. Maybe let me use that color. Okay, so this is what you can think of, honorable members. Think of water flowing inside a hose pipe or a pipe. So the water is going to flow smoothly inside a hose pipe. So you will notice that this water meter, honorable members, is going to read the same amount of water passing through there, because the water does not split in that case. That is why we say the water passing through there, it is still the same as the water passing through there, same as the water passing through there, same as the water passing through there. It made sense when I interpreted it that way, and it still does. So now let's see. In this case, what are we having in this case? So now you are having water flowing through that pipe. Can you see? When it gets there, it finds a T-junction, meaning some of the water will flow through that side, and then some of the water will flow through that side, and then it joins, and then there it continues as a combined amount of water. Meaning, good people, the water passing through there, it could be the same or it could be different when you compare it with the water passing through there. It all depends on the size of the pipe on this side and also the size of the pipe on this side. So how I normally explain it is that let me maybe use which color, that one. How I normally explain it is that if you are having water flowing in that direction, it gets there, it splits. Some water will pass through that side, and then the other will pass through this side, and then it joins. Think of it this way. If you are having, for example, more resistance this side, let's say is 20 ohms, and then here, let's say you are having just 2 ohms. Obviously, this side is resisting more, is preventing more. That means less current will flow through that side. Less current will flow through that side. Why? Because there's more resistance. It's difficult to flow through that side because there is more resistance. Meaning more current or more water will flow through this side. Why? Because there is less resistance. So it's more like the pipe this side, the diameter is smaller because it's trying to resist. But in this case, the diameter of the pipe is bigger because there is little resistance. It's not trying to resist the flow. So this will help you in a situation where you need to understand on which side are you going to have more current. So more resistance, less current. Less resistance, more current. So let me remove all of that and very quickly discuss the last type of a connection. So let's see. Obviously there, flow, split, and then split, and then it does that. So obviously, as you can see, the reading there, or the water flowing through there, is the same as the water flowing through there, flowing through there. So the water flowing through there, again, it will depend on the resistance on this side when you compare it with the water passing through that side. So obviously, if you have more resistance on this side, therefore less current. If you have less resistance on this side, obviously more current. It all depends on the values of those resistance, and you just need to know which one resists more or which side resists more. I think that will remind you of how to know which side will receive more current. Regarding the Christmas tree, what exactly did I want to say there, ladies and gentlemen? I think what I wanted to say was that every time when you think of a series connection, think of a Christmas tree. This is that a conductor, and then you are having the light bulbs there, light bulbs there, light bulbs there, light bulbs there. Can you see? You are having those resistors or the light bulbs connected in series. Because if you are having your switch there, if you just turn it on, at the same time, all the lights will glow. You just turn it off and then everything goes off. That's what I wanted to say regarding a Christmas tree. Those light bulbs that we normally use on a Christmas tree. That's if we still have those type. So it will make sense when I explain a different scenario. Remember, guys, I'm just guiding you in terms of how I cramped these things. You might need to find your own way of cramming these things. I firstly cramped, and then at a later stage, that's when they made sense, and I adjusted my cramming accordingly so that it suits my correct understanding. I'm just giving you guys a guide of how I cramped this thing. So that's all that I wanted us to discuss regarding the current. So let me slide to my next slide. Okay, so let's see. In this case, honorable members, what are we going to be discussing there? Can you guys see? Important. We have discussed the current, so now we are going to be discussing the resistance. So everything that I'm going to be talking about is now with regards to the resistance. But wait. Can you guys see there? I've got another nice drawing there. I'm pretty much sure that you guys can at this stage predict that I am going to tell you a story there. A very nice story again. So let's see. What exactly are we talking about when we talk about the resistance? In short, honorable members, the resistance refers to the material's opposition to the flow of current. That's what we talk about when we talk about the resistance in short. And here we've got the formula which says the resistance is equals to V over I. And the resistance is measured in ohms. I'm pretty much sure that at this stage, most of you guys are aware of that. So let's see. Again, that same type of connection here, which is called series connection. So let's see. In this case, how do we calculate the total resistance? Meaning, when it comes to a series connection, the total resistance, it's actually equals to R1. You need to plus it with R2. It is as easy as that. Let's not even complicate it. Let's not even complicate it because it is that easy. And very quickly jump onto the parallel connection. When it comes to the parallel connection, honorable members, that's where to calculate the total resistance, you are having that formula which says 1 over R tot, it's equals to 1 over R1. that you plus it with 1 over R2. This formula, it's not limited. It all depends on how many resistors you are having connected in parallel. So if, for example, you had another resistor there still connected in parallel, let's maybe it's R3, you are still going to plus with 1 over that R3. If you had the fourth one, you are still going to do the same. So let's see. That means the same applies when it comes to that type of a connection being a series connection. If we had R3 there, you are still going to add R3 there. Just remember that, honorable members. So now let's see the last type of a connection. Remember, honorable members, we are talking about the resistance in this case. So now here, this is where we are talking about that type of a connection where you've got a parallel connection, and within that parallel connection you've got a series connection. So the question is, how do we calculate the total resistance in this case? So again, R total, what we know is that for a parallel connection, this is the formula. But can you see, within this parallel connection, we have a series connection. We do know very well that to calculate the total resistance of a series connection, there is the formula. That is why I'm saying within a parallel connection, we still have a series connection. I hope it makes sense, honorable members. So that means for you to calculate the total resistance of a parallel connection where you still have a series connection, you can firstly add these two so that you have a combined resistance, which now looks like that one there. Having this one being, for example, that one there, then you can easily apply the normal formula. I'm telling you guys, it is not that much complicated. You just need to understand it in this way that I've explained it. But remember guys, it might not make perfect sense at this stage. This is just me taking you through the notes that I've always had for me to tackle questions related to electric circuits. You just need to remember all of this. It might not make sense as I've explained, but just be aware of this information because it's what you need. I think before we move on to the last part of our notes, let me explain there what's going on. Remember guys, this is me during my time and saying, okay, if we've got a house, it's easier to say within a house, possibly we are having a parallel type of a connection. It might be parallel, and within that parallel you still have a series connection. This is a garage of that house, and then now this is the main house, there is the door, and then you are having room number 1 there, this is room number 2 there, and then here you are having a, what is it, maybe let's say sitting room and dining room. So it only makes sense to say when you are having a parallel connection is so that when you switch off, there's the switch, when you switch off there, you just want this light bulb only to switch off and the rest remains as they are. And again, you want a situation where when you are in room 1, if you switch there either on and off, you want the other bulbs to remain as they are. You want a situation where if you are there in room 2, if you switch either on and off, you only want to make changes to that light bulb alone, and not all of them like a Christmas tree where you just switch off once and everything goes off. That's where you try to compare parallel and series. I'm just not sure if it makes sense to you, honorable members, but I'm telling you, at the time when I was trying to study these things by myself, they made perfect sense to me. And that's how I ended up fully understanding electric circuits, through that simple interpretation, which is something that I had to discover by myself just so that they make sense. But when I'm in class, I never talk about a house, I never talk about a Christmas tree. That was just for my personal understanding. I think it's worth it for me to explain to you, because it is this type of information that helped me to get distinctions in not only physical sciences, but I did the same. When I say the same, I mean I approached other subjects in the same manner. And to tell you the honest truth, I did get distinctions in other subjects using the same approach. So I hope it actually helps you to have a better understanding of what is meant, or the difference, or how to differentiate between a parallel connection and a series connection. So that's what I wanted to actually talk about with regards to that house and this light for resistance. So very quickly, let's move on to the next, which is the last part of our lesson for today. What are we having there? EMF. The EMF, important. We have discussed the current, we have discussed the resistance, and then now, lastly, we are going to be discussing the EMF. Good people, the potential difference. Someone might be wondering, what exactly are we talking about when we talk about the potential difference? There, it's a definition. So let's see. Work done per positive unit charge to move charge from one point to another. It is as easy as that. Just in case if it comes in a multiple choice type of questions, just remember that it might be given to you as a definition and you just need to choose. So here is the formula, honorable members, which says V being the potential difference, it's equals to W for work over charge. That is the formula for calculating the potential difference. So very quickly, honorable members, I think it's worth it for me to explain the EMF and again the V, the potential difference, because I used to get confused to say, what exactly is the EMF? Here's the difference. So the EMF refers to the voltage across cells. Good people, when no current is flowing. Then let's compare it with the V. The V refers to voltage across cells when current is flowing. Can you see? In this case, that's when the current is flowing. And this is how I used to claim it, honorable members. I used to say the EMF actually refers to a new cell or a new battery, brand new. And then V refers to a used battery or cell, or a battery or cell which is in use. It was then very much easy for me not to stress about that, but remember it that way. So that means if you connect a cell or a battery while it is still new, maybe it is 20 V. While it is still new, honorable members, it has what we call the EMF being 20 volts. Then once you connect it, it might no longer be 20 volts, but you might find that maybe it's 19.5 volts as an example. So this 19.5 volts, it is therefore the V. So that means there was a loss of 0.5 volts. That's when we talk about internal resistance. But at this point in time, remember, honorable members, I'm just taking you through the general notes. I do not want to complicate anything there, because you firstly need to understand what I'm explaining now, and everything else is going to make sense at a later stage. But for now, just be aware that we've got what we call the EMF and we've got what we call the V. Very, very much important, ladies and gentlemen, on that one. Hey, I also have a very nice drawing there. I am definitely going to say something about that. So now let's see. Just like we have discussed previously, let's see what happens in this case. Let's see what happens in this case where we are having that type of a connection. So this is what happens, honorable members. Can you see here, let's say we are having a, what is it, stove maybe, and then there we are having a fridge. So if we want to know how much the stove takes the electricity units, we connect a voltmeter there to read the potential difference across that stove. The reading that we get there, let's say maybe if it's 3 volts, that means the stove is using 3 volts. It's more like the stove is showing 3 units of electricity, if maybe I can explain it that way. And again, there we connected on the fridge, so that means we actually want to know how much of electricity is the fridge showing. Maybe we see that, okay, the fridge is not showing too much, it's only showing 1.5 volts. So if we want to know the total electricity that was used by those resistors, obviously it's going to be electricity charged by the stove. We plus it with the electricity charged by the stove. That's how you calculate the total electricity or the total V in a series connection. Very, very much important, ladies and gentlemen. So if again you think of that Christmas tree where you are having those lights connected on just one conductor, so that means this light bulb will have its own V that it is showing. If obviously is the same type of light bulbs, all of them are just going to have the same V. And if you want to know the total V, that means you will say V of this one plus V of this one plus V of this one plus hey, you get it? If you don't get it, forget about it. Okay, so let's see. Now, let's discuss this next part, that one there. something interesting there, honorable members. It says the total V in this case, which case? In this case where we are having a parallel connection. In this case where we are having a parallel connection, the V across 1, what is 1? That one there. They say it is the same as the V across that voltmeter 2, which is that one there. And again, it is the same as the V connected there. So this is a special situation where in a parallel connection, we know that the V connected across that, it is the same as the V connected across that, which is the same as that V there. I'm telling you guys, it is as easy as that. It might not make sense now, but trust me, it will make perfect sense when we solve exam type of questions. So very quickly, let's move on to that type of a connection where you are having a parallel, and within that parallel you are having a series connection. So in this case, the V total good people, V total in this case I just noticed something there which needs corrections. Yes, so there it's actually not a plus, but it is equals to. I'm just hoping that you guys will remember that. But one thing for sure, I will correct it on the notes as well. So let's see, what am I saying there, honorable members? So what I'm saying is, in this case, you are having that V3. Yeah, I notice I didn't choose the correct. So you are having that voltmeter 3, which is that one there, which has to be the same as that voltmeter 4. Just like in this case where we said that one there, it has to be the same as that one there. The same applies here also, honorable members. That is the same as that, because this voltmeter number 3 is connected on a parallel connection. But in this case, on that other side, this is where now you add this V with that V, because now that side is connected in series, which takes you back to that formula there. It's a bit tricky. I am well aware that it's a bit tricky, but I'm telling you guys, first time it is going to be tricky, but the more you do it over and over again, that's when it's going to make perfect sense. It's not at all the times where it's going to instantly make sense, but if you have done it before, that's when it might make some sense. Remember guys, you just need to be aware of all of this information. Whether you're in grade 10, whether you're in grade 11, whether you're in grade 12, you just need to be aware of all of this information. The only difference is the level of questioning. The complexity of the questions themselves It's what differs. So that means in grade 10, you will still need the same information, but questions will be a bit more easier as compared to when in grade 11. Same as when you are in grade 12. I'm telling you, when you get to varsity, it gets even complicated. So if you want to study electrical engineering, one thing for sure, just make sure that you fully understand what I'm explaining today, and most importantly, be able to interpret these circuits. I didn't forget to say something about that. So this is what I wanted to say, honorable members. You can see that there I'm having a battery. I think there's no story there, honorable members. You just need to know that when this thing is just one, is called a cell, and two or more cells are called a battery. Very, very much important, ladies and gentlemen, over there. You just need to be aware of that. So let's see. I think I've actually gone enough with this introduction to electric circuits. I noticed there I've gone for like 51 minutes. I did wanted to complete this within an hour. I think it was worth it, and I notice we still have some time. Maybe very quickly, let me try to just give you guys some additional information. I think I have explained all that I wanted you guys to be aware of with regards to electric circuits using the tutor's nodes. Something that you just need to remember is that there it's equals to, there it's actually is equals to, yes. Okay, so now let me just slide, yes, just wanted a whiteboard there. Maybe let me try to sketch something there and say maybe we are having what is it? Can you see now we have two cells? Maybe let me connect something there, and then let me do that. So remember guys, this is just me trying to draw something there. It doesn't need to make perfect sense or be accurate. I just need to give you guys an idea of how circuits may look like and just do a very quick interpretation there. We are having that also there. Yeah, I think maybe let me say there we are having 20 volts, and then there maybe let's say we are having an ammeter being ammeter 1 and then there we are having R1. Let's say this is R2, this is R3, this is R4, and again let me connect something also there, and then that one, it is obviously going to be the voltmeter being V1. So I want to make you guys aware of something. In which direction does the current flow? Can you see this long line? That long line, you have a long line followed by a short line, is one cell. A long line followed by a short line is another cell. So that means you've got two cells. The long line represents the positive side of the cell, and then the short line represents the negative side of a cell. So these two things combined together, they are therefore called a battery, because I just said two or more cells combined together is a battery. So now let me do this. This is now how the current is going to flow. Current flows from positive side, or from positive terminal to the negative terminal. So that means it's going to be flowing like that. This is what the current is going to be doing. And then obviously when it gets there, it splits. It's going to split, and then join there again, and then it does that. Then it continues. Maybe there where it split, let me do that and say it is going to do that, and the other one it is going to do that. So now let's try to have a very nice discussion there, honorable members. Okay, let's see. Can you guys see that the current passing through there, it is passing through a series connection? So that means it has to be the same current passing through there. It only splits when it gets to that point. So that means the other will flow through this side, and then the other one will flow through that side. Meaning the current flowing through this side, when you plus it with the current flowing through that side, it has to take you back to the total current which joins there, and then it continues. Obviously the current passing through there, it is in series connection. So again, with regards to the resistance, in this case the total resistance, honorable members, it's going to be R tot. It's going to be equals to R1. R1 is connected in series, and you need to plus it with R parallel, and then you need to then plus it with R4, because that one is in series. So remember guys, the R parallel has got a formula which says 1 over R parallel. It is therefore going to be equals to 1 over R2, that you need to plus it with 1 over R3. So that means you are going to use your mathematical knowledge or your mathematical steps or rules to solve for R parallel. Let's say for some reason that one, it was 2 ohms. That one there, maybe let's say it was 3 ohms. Maybe this one, let's say it was 5 ohms. And then this one, let's say it was 7 ohms. I'm just giving you guys examples for you to know that you've actually calculated R parallel correctly. Between these two resistors which are connected in parallel, which one is the smallest? Obviously the 5 ohms. So when you calculate your R parallel, the R parallel that you're going to get, its value has to be smaller than the smallest resistance. So that means if you are having 5 and 7, your R parallel combined, these two combined, is going to be less than the smallest. So that means when you continue with your calculation, you're going to have your R1 being 2 ohms, you plus it with that small resistance of parallel, and then you plus it with the 3 ohms. Then that's how you get your total resistance, which is measured in ohms. Very, very much important, ladies and gentlemen, on that one. I think what I've explained, it does make sense, honorable members. Maybe let me try to undo. I will see up to what point and check, since I still have some time, in case if there's something that I can explain there. But I think you guys are having an idea. Okay, someone might be wondering, what about the V now? What about V? Okay, so remember guys, we've got something called V, which is the potential difference. In this case, you won't say maybe let's say the V connected across the battery. let's maybe call it V2. You won't say V2 it's equals to V1. Why? Because you still have the series connections. Only if you did not have that series connection, you did not have that series connection, then you're going to say V2 is equals to that. But in this case, that means the V total. In this case, you're going to say the V total. It is therefore going to be the V of, let's say, the microwave, that you need to plus it with the V of the fridge, that you need to also plus it with the V of that parallel connection. So that means is the V of R1 that you need to plus it with the V of R4 that you need to plus it with the V of parallel. And now this is where we say the V, maybe let's say V3, the V of the parallel. It is the same as the V of A1, and also it is the same as the V of R2. Because in this case, can you see, it is that V3 connected on that parallel connection, and within that parallel connection we don't have a series connection. So that's where it gets even trickier, honorable members. But I think what I've explained, it's actually enough for you to get started with solving exam type of questions, and I hope you did enjoy this lesson. So ladies and gentlemen, it is that stage where I am now about to sign out, but I feel like explaining this last part, honorable members, regarding the EMF and the V. So if you guys remember, we have a switch. Let's say now the switch is open. Let's say now the switch is open. That one there, removed. The switch is open. When the switch is open, is the current flowing? Yes or no? Obviously the current is not flowing. So that means this V, it is now measuring the EMF, if you remember the notes, because the current is not flowing. Now the switch is closed. Now the switch is closed. When the switch is closed, this V, it might change, it might not change. If it changes, let's say now V, it is no longer 20, but it is 19 volts. If it changes, it's because there's what we call the internal resistance of that battery. Because of that internal resistance, we lost 1 volt inside the battery. Okay, what if that EMF does not change? Exactly what you are thinking. If it does not change, and then the V, it is still 20 volts, it means there is no internal resistance. That means that battery has got no internal resistance. I think it was worth it for me to just explain that part quickly. I'm pretty much sure that you guys won't miss a lesson where I answer exam type of question papers. And also, just make sure that at all the times you firstly watch this lesson so that you have a better understanding as I'll be explaining how you answer exam type of question papers. So ladies and gentlemen, I'm just wondering if there's something that I'm missing. I don't think so. And lastly, guys, because I've taken long on this lesson, I might have explained mistakenly there and there But just be aware that what I've explained on my notes is what I've always been using. So in case if I've made minor mistakes, I will only notice as I watch this lesson afterwards. But I think most of the information that I provided, it made sense and it's going to help you have a better understanding. So ladies and gentlemen, I do thank you very much for joining. My name, wait, I need to sign out. Okay, my name is Desmond